Alright, so this video is going to cover acid-base reactions. Acid-base reactions are similar to double replacement because they behave in the same sort of way. The basic idea here is we have acid, we have base, that makes salt, and water. This is going to be something you can find in common with all of these. Acid plus base gives you salt and water. Let's take a look at, for example, of nitric acid with calcium hydroxide. HNO3 plus CaOH, parentheses twice. H combines with the OH in calcium hydroxide, and calcium combines with nitrate and nitric acid. So Ca with nitrate, calcium is a positive 2, nitrate a minus 1, crisscross that. That's where the 2 comes from. We need each nitrate's minus 1 charge, I need 2 of those. H goes with OH to make water. So remember, H2O is just HOH. Hope you see that. H on the acid, H on the acid, H on the acid, and OH on the base. We have 2 H's. So it's two H's, so it's H and H after you balance the equation. I have 2 OH's. Therefore, I can make 2 water molecules. HOH, HOH, 2 H2O, or 2 HOH. So all acid-base reactions are done pretty much the same way that we're going to deal with, at least in this class. If you were to break up things which are water-soluble, the aqueous ones, leaving the liquid alone, liquids you can't split up, you would find that the net ionic equation for acid-base reaction is always H plus OH minus makes water. This is known as a neutralization reaction because acid and base neutralize each other to make water. Here's some common acids and bases. Group 7, acid halides, HCl, HBr, HI, and so on. We have HNO3, H2SO4, HClO4. These are all examples of weak, strong acids. Formic acid, acetic acid, hydrofluoric, the ones on top here are known as strong acids. The acids at the bottom are weak acids. On the bases, we have sodium hydroxide, lithium hydroxide, potassium hydroxide. These are known as strong bases, meaning they completely ionize, as well as calcium and barium hydroxides as well. Other hydroxides are going to be weak bases. Ammonia is also a base, even though it does not have hydroxide in it, because if you put ammonia in water, it generates base as one of the byproducts. So hence ammonia is also considered a base. It's just a different kind of base, but it is a base. Let's try a couple of these examples. HCl reacting with barium hydroxide. H goes with OH, barium goes with Cl. Now the charge of barium in the group on the periodic table, barium is a positive 2, chlorine is a minus 1. So barium is plus 2, Cl is a minus 1, therefore you need to put a 2 next to the chlorine. Plus water. Balance the equation. We have I have 2 chlorines on the right, therefore I need 2 chlorines on the left. I'm going to put a 2 in front of HCl. Maybe change the color for that. 2 in front of HCl. It gave me 2 H's from the acid, 2 OH's from the base, therefore you need 2 waters on the right hand side. Case of sulfuric acid with lithium hydroxide. We have Li combines with SO4. So LiSO4. Lithium is plus 1, sulfate's minus 2. So you need to know those charges. So we get Li2SO4 plus H2O. Balance the equation. 2 lithiums on the right means 2 lithiums on the left. 2 H's, 2 OH's, 2 waters. And that's how you balance those. These are also known as the titration reactions. You may have done this in lab. Here's an example where we have some acid in a flask. We add a phenolphthalein indicator. Phenolphthalein is colorless in acidic solution. We're now going to add base from a burette to the flask until we reach what's called the equivalence point. The equivalence point occurs when the moles of acid equal the moles of base, meaning they neutralize each other. Once you reach that point, phenolphthalein will turn pink, meaning we have just enough base to interact with all that acid. A little bit, any extra base will make it turn darker and darker pink. So the goal is to make it as faint as pink as possible, meaning we have reached basically the exact amount of base necessary to interact with all that acid. Gas. There's also a section here in your book dealing with called gas evolution reactions. I'm not going to make too big a deal about this. A common example are going to be baking soda with acid or vinegar. Okay, so this is sodium bicarbonate. That's baking soda. With HCl, that's a hydrochloric acid, or at home we have used acetic acid. That's like the volcano experiment. You make a salt, like always. Plus, you make this carbonic acid, H2CO3. This is unstable, so it naturally decomposes to form H2O and CO2. This is really the only gas evolution reaction you really need to know involving acids. I'm not going to make a big deal about these other ones, but this one actually is quite. This particular example here is actually quite useful, so I would know this one. But the point is, the gas gets produced as one of the byproducts as well. So this is some common gas evolution reactions here. But the only one that I'm going to require to be really familiar with are going to be the bicarbonates and bicarbonate ones. Okay, that's like the volcano experiment you might be familiar with at home. And this is a typo. This is not right. That's a bad example. This would be like 8Cl plus NaC2 Na8Cl3. There we go. The example we did a little bit ago. The rest of these reactions are going to be classification what are called oxidation reduction reactions or redox reactions. I'm going to make this part into a separate video because I'm going to go over some content here that was not covered in Chem 1025.